I'm loud enough, I think. Okay. Oh yeah, that thing. Good call. Yes, I had to turn it on. It was the first one did have no audio, right? Okay. Yeah. No, I fixed that. Someone in my other class mentioned that. All right, we're gonna get started. We have a little surprise for you today. We have a doctor in the house. Okay, Dr. Flynn Murray. She is leading up the EM Learning Center. Okay, recent graduate in the civil engineering department. Okay, so I'm going to give it to her to kind of give a little spiel about the EM Learning Center and how badass it is. Okay, so after you.
Alright, did anyone use the Learning Center last semester with Daruk? Was it helpful? Unfortunately, Daruk is now the grader for your class, and he has not be in the Learning Center. He's so kind. So reach out to him if he isn't too busy grading. I know that's another option for you. I think you have his information, but he's so great. But anyways, he's not in the Learning Center anymore. You should still come to the Learning Center because it is a very good resource for you all. This gentleman just told me this is probably one of the harder classes that you're going to take in your curriculum. And so help is good. And it's a good place to work with each other. It's a good place as you're working along through a problem to be consistent so that you're not you don't get to the end and find out you did it wrong. You can kind of get help along the way. I updated the website so that hopefully it's easier to find out what's going on. So you have access to the website on D2L. You scroll down and you click on the 205 or the 208 drop down menu. That's where you are. That's scheduled for right now. I'm happy to adjust that for you. If that doesn't work for you, if there's better times, we would happily accommodate you. So my email's on that website, so always feel free and tell me good, bad, indifferent type stuff I would like to know. Arash is now going to be the main tutor for 208 in there. He's really smart. He gave me 2 picture options. I liked that one. He's having more fun than the other one. He was behind the president.
I like Al Pacino movies.
Yeah, he likes Al Pacino movies. I was pretty happy to see that as well. So, he's really nice. He's smart, but just work with. He knows his stuff. And he's kind of he's good. So he'll definitely be able to help you. If you're in there when he's not there, hopefully other people will help you. But if he's here, you can definitely count on to be on top of your material. We're also trying this new one-on-one tutoring idea, which I haven't implemented for your class yet, but I'm going to work on it. And if you're interested in that, send me an email because it would be an opportunity to not just kind of go in there and get homework triage, but maybe get a little bit more help with concepts and staying on top of materials. You feel like you're getting behind, and kind of diving into that. So Learning Center is pretty awesome. You should go and then go before you're like, oh boy, this class is hard.
Yeah.
But it's good stuff, and it's this class is beautiful, so enjoy it. Tim is very smart.
You don't want to see me. Well, actually, you won't see me next semester if you have the privilege of taking this class again. You will actually see Dr. Murray there. So.
Just stuck with me, and ideally in a different room where I don't need you to lift me up on.
Yeah, exactly. So we have Arash, but we also have Daruk, who has been grading, as Flynn mentioned. He also, I need to get him to give him a little introduction in an announcement on D2L, which I will do that. So you can always email him also for homework questions. He will be doing the grading aspect of this class. And then also myself, right? I've got office hours from 10 until noon, but honestly, email me or just swing by my office. I'm usually there Monday, Wednesdays, and Fridays most of the days. So swing by and get some help. This is a hard class. This is some of the hardest stuff. This weeds out whether or not you want to put in the effort, okay? It's not about being smart. It's about just putting in the effort to make it through, okay? So, anything else, Flynn, that I missed?
Yeah, just practicing. It just takes a lot of practice and homework for. And so get help if you're doing that.
So if you get lost and you don't know the website, out on D2L, there's a content section that's all about the EM Learning Center. I've posted the current schedule that's up there on the website, as well as a little blurb here about the EM Learning Center with Flynn's contact information as well as the website, okay? So.
And if you don't like it, there's also a Google form with QR code in the Learning Center. You can give anonymous feedback too. Fine. Keep me informed if you can do better. Yeah.
Okay.
I need help.
You want some help?
Thank you.
Yeah. No, that's fine.
Sorry. You guys get a little break. Tim pushes me.
Posted on like 7th grade.
All right, let's do this. Okay, any questions about the Learning Center? Okay, highly recommended, okay? Highly recommended. If you don't go to the EM Learning Center, as we introduced everybody at the beginning of the class, right? There's a lot of people in your same situation, maybe have some same hobbies or interests, right? Start finding those people, spending time with those people, working on homework together and whatnot, okay? 2 minds are better than 1. All right. So, on Monday, we started talking about shear stress, right? The intensity of the force parallel to a cross-sectional area, right? Normal stress is the intensity of a force perpendicular to a cross-sectional area, okay? We went through an example. We had a couple glued pieces of wood to each other, right? One shear plane, one location with which we have transfer of force parallel to a cross-sectional area. Calculated that we had 5.4 psi of shear stress, right? Average shear stress, because we're assuming that it's uniform over the entire cross-section, right? That entire area. Then we started this example, which was a clevis. As I mentioned, you can find a lot of them in the engineering building or other buildings on campus, okay? We were asked to find the shear stress in the bolt. So in order to do this, as we do in most of our, or pretty much all mechanics of material problems, we do a free body diagram, right? We need to know what the internal force is. That internal force then allows us to calculate the internal stress or the intensity of the force based on the cross-sectional area over which it acts. So in this case, we drew a free body diagram of our clevis. I cut the clevis so you could see kind of this force transfer, right, through the center plate, right? We have a full force P. And as we run through the clevis, well, we have 2 sections of clevis. Because we have symmetry, these forces get split in half. So we have P over 2, or 75 pounds, acting on each of the legs of our clevis. From this point, right, now we have forces. We were given the diameter of the bolt, so we have area. We know we need to calculate shear stress. Right, or P over A, right, force over area, the intensity of the force, stress. So we can calculate this in 2 different ways, right? We can calculate it with respect to the force being this P over 2, or the force being our entire P. Why is that? It's because, right, we have 2 shear planes, so we could either cut out another free body from this diagram. Right, cut off one of the legs of the clevis, and we're looking at what's going on right at our shear plane. We would have our force P over 2, right, trying to shear that bolt off. See if we can find a different color, right? Or we could look at a different free body, right? And look at both of our shear planes together. And hopefully we should get the same answer. All right, so if we look at first, right, one shear plane. Our free body diagram that we're looking at, right, is that upper one, that upper circle there. Might have, if we looked at a cross section, right, we're gonna have our force P over 2 acting on the bolt, right? It's our P over 2 that we calculated before. The bolt itself, it needs to resist that, right? So we've got a P over 2 acting on the other side of the bolt, right? That's our other P over 2 would be acting right here. Something like that, right? We know the diameter of this is 5/8 of an inch. So now we have our force and we have our area. We can calculate our shear stress, tau, would be our force, P over 2, divided by the area. Well, if we know diameter, pi over 4d squared, which we get 150 pounds, that was P, divided by 2, all over pi over 4, times 0.625, 5/8 of an inch squared. We get 244.5 PSI. That was made out of wood. That might be an issue. If it's made out of steel, that's nothing at all, okay? Usually steel is like 36,000 PSI. So we'll talk about that when we talk about material properties, but so not a lot for steel. As I mentioned, we can look at this a second way. Right? We can look at two planes. Right? The light green circle there. So now we have two surfaces with which the force is transferring across, trying to cut this bolt out of the clevis. All right, so now we've got the full force P acting off to the right. And we have 2P over 2 acting off to the left, right? That would be our two guys here. P over 2, which would mean there's a P over 2 over here, right? Resisting it. The clevis is pulling off to the left with P over 2 on the top and bottom. The plate is pulling off to the right with just P. It's going through two shear planes, which we would call this double shear. So in this case, again, now we've got tau is force over area. Well, now we have our full P load Well, now we have two shear planes. So we have 2 times pi over 4 d squared, which is 150 pounds, divided by 2 times pi over 4 times 0.625 squared. What do we get? We get 244.5 psi. Right? So as long as the free body diagram is appropriate, yeah.
Where are you getting the pi over 4?
So the area of a circle with a diameter d is pi over 4 d squared. Or it's the same as pi r squared, but pi r squared, you could do it with the radius. Not as popular of a method to calculate the area of a circle, but yeah. If you were to substitute in 2r into pi r squared, right, you'd have to divide by 4 to get rid of that 2 squared, which was 4. So yeah, so it's just force over area, just as we've talked about, to get the shear stress. You can either look at one of the planes, right? Or you can look at both planes. One plane, right? And in some cases, we have only one plane, like our first example, right? This would be a single shear plane across the 2 pieces of wood. But as we looked at a different type of configuration, right? We've got 2 shear planes acting in this. This would, you would say that this bolt acts in double shear. So this would be a double shear failure. Right? You can imagine this clevis is acting on the outsides of this bolt, right? The plate is acting in the center. If you pulled hard enough, right, the stress is the same on both, so it should fail at the same time. It would just slide that inner piece of bolt out from between the outer pieces of the bolt, right? So that'd be a double shear failure. In the homework, this is a type of connection that's in the connections on the second problem, okay? They're all double shear connections. So that means you have 2 shear planes, right? Any questions about that? Yes.
Can you just explain the cross-section free body diagram again? Just like the forces?
On the single shear versus the double?
1 and 2.
Yeah. So if we looked at, this is our clevis. This is our plate. And we had some sort of pin or bolt putting these 2 together, right? And we'd have some sort of load, P in this case, right? Was our 150 pounds. So to pull out a free body diagram, we could legitimately cut this anywhere we wanted, right? That's the essence of a free body diagram. You're pulling out a free body, and you're imposing on that free body the forces that are acting on it externally, right? So we have, this is a free body, looking at the entire clevis connection assembly, okay? Which we have forces on the left equaling the forces to the right. So this thing can't move anywhere, right? If you did sum of the forces in the x. So anywhere that we cut this, we still have to maintain that same equilibrium. So if we were looking at what we did first, was we cut out this section. This would say, we'd say this is our free body diagram, say number 1. And when we cut that out, it looked something like this. Now we have P on the right-hand side, right? We know what that is. And then we have two internal reactions, right? We have two forces that are going to be in the yoke of our clevis, right? If we cut that clevis off right there, there's going to be some sort of internal force in the top section and the bottom section, right? So from there, we know we've got our bolt sitting here. We have some of the forces and some of the moments, right? We need a coordinate system here, which I did not put in. I'm going to do X, Y, looks something like that. Okay. Well, our forces are all acting in the X direction, right? So if we did sum of the forces in the X, they must equal 0, just like they equaled 0 in the overall free body diagram. So we got P to the right. Our coordinate X is positive to the right. We've got R1 to the left, right? So it'd be negative. And R2 to the left. So we know what P was. We don't know what R2 and R1 were. All right, so we need an additional equation. All right. So we need to use some of the moments. So if we drew a line through here, right, we would have some sort of distance x that separates our two reactions in the yoke with the reaction in the plate, right? And the sum of the moments about any point on this free body diagram have to equal 0, right? And so I would say sum of the moments about, I'm going to pick a point right here. Maybe we'll call this point A. So sum of the moments about point A equals 0. Well, if we use the right-hand rule, we can start with reaction 1. Curl our fingers in the direction of the force R1. We get our thumb pointing outward, so that'd be a positive. So I would say this is R1x. Right, positive. P, we move down our free body diagram. P has no moment arm, right? No distance between it and this point with which we're summing the moments about. So there's 0 moment there. Then we have R2, also times x, right? The clevis is symmetrical. So this distance x and this distance x are the same. So we end up with this equation that R1x minus R2x equals 0. The x's cancel out, and we end up just with R1 equals R2. Well, if R1 equals R2, we can sub R1 equals R2 in this equation. You end up getting P equals 2R1, or P equals 2R2. So you end up getting R2 and R1 equals half of P, right? So that's how we got our first reactions in our first free body diagram, right? That's how we got this free body diagram in the first place. I kind of jumped a little bit ahead there, okay, assuming some of that was coming back from statics. Now when we look at our single shear plane or a double shear plane, right, now we're going to cut, I'm going to cut it something like this. Okay, this would be free body diagram number 2. So looking at our first free body diagram and knowing we want to just cut out this top portion, and we know that R1 now is P over 2, which I'll write that down here. Therefore, R1 equals R2 equals P over 2. So if we draw another free body diagram, this time we're going to draw just our top portion and do something like this. We now know that we have P over 2 acting to the left. Well, we need some sort of extra or internal force, right? There's going to be some internal force in this bolt wherever we cut it. Might call that reaction 1. We know that to maintain equilibrium, the sum of the forces have to equal 0, and the sum of the moments have to equal 0. So sum of the forces in the x, if we gave ourselves a coordinate system x and y, right? Whoops. We'd say 0 equals minus P over 2, right? It's acting to the left, which is in the negative direction, plus R1. I assumed R1 is acting to the right. We end up getting R1 equal to P over 2. Does that kind of help you out with where we get the first shear plane forces?
Yeah, I was just like trying to picture just the one plane you do like a circle, like.
So I was looking at it like looking downward on the top of, if you were to take this clevis and rotate it 90 degrees, and then you're starting to look at basically from the top down on the top of this bolt, right? The visual you would see here would be a circular cross section where that bolt comes through. Does that make sense? And so similarly, we could do the exact same thing looking at now cutting this out. Right? This would be free body diagram 3. Okay? In that case, we know the reaction in this bolt, right? We know the reaction in the plate. The only reaction we don't know is the one that's in this bolt. Well, if this is P over 2, that's P. This has got to be P over 2 based on some of the forces in the X, right? Okay. Any other questions? That's great. Happy to run through whatever you want, okay? Oh, I'm supposed to tell you this. Glad I came back here. There's a pizza social in the sub. ASCE, I think, all of the, ITE, AGC, ASCE, EWB, and GeoCats all pooled together, and they're putting together a pizza social in the sub ballrooms. So if you're around today, around 4 to 6, okay, free pizza, go check it out. All right. Now that we have determined what shear stress is, and now we know what normal stress is, right? We have intensity of a force that's on a cross-section normal to the applied load. We have the intensity of a force on a cross-section that's parallel to the applied load. Well, what happens if we're somewhere in the middle, right? There's times in which we're going to have a plane that we're going to look at that's not perpendicular to the applied force, or that plane is not parallel to the applied force. It's somewhere in the middle. So if we drew a square or a little box section here, what does that look like? So if we had a block of material, and again, we applied some sort of force P to it. And if we applied force P on the right-hand side, we'd have to apply a force P on the left-hand side. Make sure we have equilibrium. If we had dimensions of this block, say it was D tall, and B wide. And had a length L, okay? We have calculated normal stress, right? Which normal stress is the intensity of the force to an area that's perpendicular to the applied load. So what does that mean? Well, that means, I'm trying to find a good color that's not. Right, we were looking at the stress on a cross section that looks like this, right? It's normal to our applied load P. Right, our angle here, which we would call beta, is 90 degrees, right? That would be the area over which we would be calculating the stress if we were calculating normal stress, right? So normal stress, average or sigma average, is P over A, which in our case, for this block, would be P over the cross-sectional area in this case, which would be D times B, right? This would be normal stress. Okay. We've also looked at shear stress. Right, so if we did another block here, let's assume it has the same loading. We've got P. Whoops. P acting off to the right, P acting off to the left. Same dimensions. Beta in this case equals 0 degrees, right? If our reference plane was the bottom of our block, right, we have 0 rotation of our plane. If we're looking at shear stress, right? So this would be the cross section that is parallel to the applied force, that purple there, which we would call tau average, which is again P over A, where A is the area parallel to the applied force. So now we have P over BL. Right, this is shear stress. Well, now what happens if we take, oops. Didn't hold this long enough. If we had same dimensions, what happens if we look at a plane that is not at 0 degrees or at 90 degrees, but somewhere oriented in the middle? All right, beta not equal to 0 degrees, not equal to 90 degrees, but somewhere in the middle. All right, this would be a inclined plane. Well, if we were to cut our section, our block, if you will, we drew a free body diagram, right? We plucked this portion, this free body out, the left-hand side of our inclined plane. We drew a free body diagram. We're going to have P on the right, well, we're going to have P on the left to maintain equilibrium. But that P on the right we're going to find has now components, right? Components of P that act parallel to the surface and normal to the surface, right? So sigma and tau now become components of our resultant force P acting at some inclined plane. Right, so P has components of both sigma and tau. What does that look like in a better presented slide? Well, it looks like this. Okay, this came out of the textbook. Right. So if we look at part B here, right? So again, looking at our block, we've got forces P acting on our block to make sure we have equilibrium. All right. If we looked at a plane that was cut through this block, AA, right, we're going to have an area associated with a cross section now that's perpendicular to P, and because of that, we're going to get normal stress. Right. If we look at cross section cut at BB, because our P is still horizontal, right? The resulting stress across this cross section is going to be horizontal, but that resulting stress has components that are both normal to the surface and parallel to the surface. So we end up getting this normal force and a shear force, right, that are components of our P, which create a normal stress, right? Normal stress definition, intensity of a force normal to a cross section, right, or an area. So we're going to get a sigma n, or a normal stress acting on our surface. And we're also going to get a shear stress acting on our surface, right? Because we now have components of our P, our resultant force, that act along the plane and perpendicular to the plane. All right, so for D, E, and F, P is broken into components of sigma, right, which is our normal, and tau, which is parallel. Right. If we were looking at this, and we wanted to know what N is or V is with relationship to P, what would it be? It is P sine theta. What would that give you? V or N? V, right? Yeah. Opposite. SOHCAHTOA thing. Right? Something that you remember for the rest of your life for some reason. P sine theta gives you V. P cosine theta gives you N. So we've got N equals P cosine theta. V equals P sine theta, right? Well, if you remember from up here, we had this other angle we called beta, right? Beta was measured to the horizontal on the back side of this plane. Well, if we draw in beta, Beta would be then this angle, right? If we wanted to find a relationship between beta and theta, any idea what that would be? If we knew beta, how could we find theta? Or vice versa. They're complementary, right? So one's 90 minus the other. So we would say that beta equals 90 minus theta. Right? Well, what does that mean about our little relationship we said here? Got a 50-50 shot. What's N? P what? Perfect. Woo! Killing it today. Just opposite, right? Now you can do the homework, right? The last problem in the homework. But we're going to go through some more of this, a little more examples, okay? There's a little bit more to it, right? So if we're looking at this now, right? We can figure out what our forces are, N and V, normal force, shear force, right? But stress is a function of force and the area, right? So we no longer have this simple height times the width, right? Our area is going to change as we have this inclined surface, right? It's going to get bigger the shallower that angle gets, and it's going to stretch longer and longer until finally, when beta equals 0, it's the full length of our block, right? So it'll go from the depth to the length, right, times the width. So if we look again here, we'll start with another block. We have some forces P on it. We had a dimension D. Whoops. Had some dimension B, right? Width B. If we cut this, and a length L. If we cut our block at some incline, and we wanted to know what is the shear stress and normal stress along that incline. Why the hell would we even cut the block like this in the first place? Well, a lot of times we glue shit together, right? We weld things together, epoxy things together, okay? So we don't always just do a butt joint, right? Put two things straight up, normal forces together, right? Sometimes we don't just lap things together, right? We might have to weld things at an angle, might have to glue things at an angle. So we want to know what is the stresses along that plane, right? Maybe a connection plane. So if we look at that cut, right? Now we again have our normal force, our shear force acting along that plane. And as mentioned, right, as our beta changes, so does area. All right, if we looked at the area of that cross section, which we need to not only calculate our shear stress, but our normal stress along that inclined plane. So we really want area as a function of beta, right? We want to just be able to look at an inclined plane, say, all right, beta is 35 degrees. If we know what the length of our block is, the height of our block, and the width of our block, we can, and the force in our block, we can figure out what is our normal stress and our shear stress. All right, so if we take another section out of our, right, if we looked at just an incline, which now becomes a triangle, right? We were to just cut out this little section of our block, it would have a height of D, right? No matter what, as that incline cuts, it's got to cut through the entire cross section. So the height of that triangle is always going to be the height of our block, right? We've got to cut completely through it. I'm going to call this H, which is the length of our cut, right? Area being length times width. We want to know what the length of that plane is, H. Well, from trigonometry, we could say that H is D divided by the sine of beta, right? Because H sine beta is D. So H is D over sine beta. Well, if we wanted to know what the area of that cut cross section is, right? It's going to be the length of that cross section times the width of that cross section. All right, so we have B times D over sine beta, right? That's the width of our block is B. The length of our inclined plane is D over sine beta. And maybe we'll call this A sub n. We'll call the area of our block, our cross-sectional area of our block, D times B. Well, we have D times B here. So now we could say, well, the area of the incline, A sub n, is really A over sine beta. Well, now that we know the area of our incline, right, and we know what our shear force is and our normal force is, yeah?
You just substituted B times D.
As A, yes. Like I just drew it right there. Right, so the area of our cross section is the width times the height, B times D. So we know from up above, our forces are P sine beta. Our shear force is P cosine beta. Right? Well, now that we know the forces, right, normal force and shear force, and we know what the area of the incline is, A sub n, we can figure out all of our normal stresses, right? Sigma n, n over A sub n. This is P sine beta over A over sine beta. We end up with P over A sine squared beta. This is the same as saying P over 2A. If we do trig identities, you guys remember all of that, right? Not expecting you to know that, but just know that this is the one, right? That's the easiest to do in your calculator. P over 2A times 1 minus cosine 2 beta. That is our normal stress on an inclined section, right? With angle beta. And here, so that you guys have it, A sub n, tau is V over A sub n, right? Is P cosine beta, again over A sine beta, get a bunch of stuff. 2a sine of 2 beta. Now you have everything to do the homework, okay? Do a week from today, 5 p.m. There'll be a quiz next week also. I'll post it. And I'll let you know more about that later on. All right, we're going to start strain on Friday.